Good morning, everybody. Today we will continue with Chapter 10, Dynamics of Rotational Motion. What we have is in this Chapter 10, we will talk about torque produced by a force in rotational motion, and we will investigate how the net torque on a body affects the body's rotational motion. Remember the Newton's second law, net force on a body. And here in the rotational motion, we will investigate the net torque on a body. Very important part of this lecture. We will analyze the motion of a body that both rotates and moves, okay? This is translational motion or linear motion, and this is rotational motion. And a certain body has these two types of motion, and we will analyze this behavior. And in the second part of this lecture, we will investigate the work and power for rotating bodies. And finally, we will finish with the conservation of angular momentum. Let me tell you here at the beginning that you will not learn something new, okay? This information, which we will see during this chapter, more or less discussed before, okay? So in the linear motion, we have discussed velocity, we have discussed acceleration, we have discussed force, we have discussed the work and power, okay? And we have discussed the Newton's laws. We have discussed the net force is zero, first law. We have discussed the net force is different from zero. And we have also discussed the action-reaction pair of forces. So we have this information from previous chapters, and now we will use this information, and we will also get some new expressions for the rotational motion within this chapter. So let me start with this one. Here you see a bolt, okay, and you would like to loosen this bolt. This is the axis of rotation of the bolt. This is the origin. So you would like to rotate this bolt around this rotation axis, and you are using a wrench, let's say, okay? And you are applying different forces. You applied force to the A point here in this direction, to the right, and you applied a force to the B point here, okay? Again, to the right side, and you apply another force to the same point, but the direction of the force is along the axis of rotation. So which one is useful? Force close the axis of rotation, not very effective, okay? In order to loosen this bolt, you have to apply huge force, okay? Because lever arm is very small. I will discuss all these things. And if you apply same force far from the axis of rotation, then this will be more effective to rotate this wrench to loose this bolt. And if you apply this kind of force, this force C here, directed toward axis of rotation, this will produce no effect on the rotation, okay, because it is passing through the axis of rotation. We will discuss all these things during this lecture. Now let me define what is the line of action, what is the lever arm. Here you see a body on the right side, okay, this is a body, and here we have O point, and you apply forces on different parts of this body. This is, for example, F1 in this direction, and here we have F3 in this direction to the left, and here we have F2, okay? So what is line action of a force? Line action of a force is this one, okay? You can consider a line along the force applied. Again here, line of action, this one, and here for the force 2, this is the line of action, okay? So this line along the force. And what about the lever arm for a force? Lever arm is this one. if this O point is the rotation axis, so what is the distance of line of action of the force to this rotation axis? Okay, this perpendicular path, this one is the lever arm, or let's say the path or the line perpendicular to the line of action of the force is given with the lever arm. So what do you see here? Here we have F1, and this is the line of action of F1, and here we have lever arm of F1, and here we have F2, and this is the line of action of F2, and here we have a perpendicular line. This is the lever arm of F2, okay? So what do you see here? We have F3. F3 is directly applied through the point O, so the lever arm and hence the torque are 0. There is no lever arm for this force. The torque produced by a force is given with this expression: the force times lever arm. It's lever arm, okay? Perpendicular path to the rotation axis. So look at this F1. F1 has certain force, and then it has certain lever arm, and then put these numbers here, then you can calculate the torque produced by F1, and this object will be rotated, okay? And here we have F2, it has certain lever arm, but in case of F3, there is no lever arm, and the L is here 0 for the F3, then there will be no torque due to this F3. Then let me continue with the 3 ways to calculate the torque. We will continue with the same mechanism, line of action and lever arm. Here we have a force. Force is applied upward, okay, this is the F, and this is the distance between the force and the rotation axis, point O, okay? So this distance is given with R. And what about the torque produced by this force? In order to calculate this force, you can just use this expression. Torque is given with F times L, okay? But what is L here? Remember that the L is lever arm, and this lever arm, this one, not this R, not this blue line here. It is not blue line. Lever arm is this one, let's say this purple one, okay? So lever arm must be perpendicular to the applied force, perpendicular to the line of action of force, okay? So then you know the force. If you know this lever arm, then you can calculate the torque. In case of this example, if you don't know the L, you can calculate the L, lever arm. Here we have R, here we have phi angle, then lever arm can be given with this expression, R times sinus phi, okay? Just put R times sinus phi here, then you can calculate torque again. Another method to calculate the torque, here we have a force upward, applied upward, and then this force has two components. One is tangential component to this rotation axis, okay? And F tangential is given with F times sinus phi if this is phi angle. And then this force has a radial component, F radial, which is given with F times cosine phi. So then you can also write this one. Look at this one. This F radial does not produce any torque because lever arm is 0. Line of action just passed through the rotation axis. But this tangential force, this one on the left side, has certain lever arm, which is given with R. Lever arm for this force, tangential force, is R times F tangential, okay? If you write F sinus phi for the F tangential, then you will get the same expression. Any question here? So then let me continue with the direction of the torque. Torque can be expressed as a vector using the vector product. So look at this one here. In the torque definition, we have sinus phi, okay, r times f times sinus phi, and we can write this one in this form. Torque is a vector, and this r vector from origin to where f acts. This is the r from the origin to the point where the force acts, and then we have vector product. Okay, so by using this expression, you can find the direction of the torque. Look at the example here. This is the direction of the r, okay, and this is the direction of the force. So what about the direction of the torque? So you can find the direction of the torque by using the right-hand rule. So here, look at this picture on the right side. Here we have a bolt, here we have a range, let's say, and then here we have r, okay, distance from the origin to the point where force is applied, and force is out of page, okay, from page to us, let's consider, and then just use your right hand. Your four fingers are showing the direction of the r, and then you curl them along the force direction. Then your thumb, okay, your thumb will show you the direction of the torque, okay. Now let me show you very easy example applying a torque. Here there's a pipe fitting, okay, and you would like to open this fitting, let's say. To loosen a pipe fitting, a plumber slips a piece of scrap pipe, a cheater, over his wrench handle. So he puts something here in order to stand over this part. He stands on the end of the cheater, applying his 900 Newton weight at a point 0.8 meter from the center of fitting. So the distance from the force applied by the guy to the center of this fitting is 0.8 meter, which is given in the question. The wrench handle and cheater make an angle of 19 degrees. This is the angle here, 19 degrees. Okay, find the magnitude and direction of the torque he applies about the center of the fitting. So here on the right side, we have the free body diagram. This is the rotation axis, okay? And this is the distance between the force and this O position, which is given as 0.8. And this force is due to the weight of this guy, 900 Newton. And this force has two components. One is F radial along this direction. The other one is F tangential, okay? F radial does not produce any torque because it has no lever arm. It is line of action passing through the rotation axis, let's say. And here we have F tangential. Look at this formula, F tangential times R. Then if you can calculate F tangential, and if you know the lever arm, then you can calculate the torque. So what about the direction of the torque? Then just apply the right-hand rule. This is the direction of the R, okay? And this is the direction of the force. Then this is the direction of the torque. We can find this expression, okay, this right-hand rule. So here we have the calculation. Finally, the torque is calculated with this one. You put the F tangential, you calculate the tangential part of the force. This part is given, angle is given, then just put the numbers here, and the lever arm is also given, then you can calculate it. Okay, and let me get a relation between torque and angular acceleration for a rigid body. This term is very important, which I have explained during the last lecture. Rigid body means that during the rotation, during the movement, its shape does not change, okay? Don't forget this. So we have learned angular acceleration, and we have also found relation between angular acceleration and linear acceleration during the last lecture. And now I will explain the relation between torque and angular acceleration. Here we have a picture. Look at this picture on the left side. This is the x-axis. To the right side, this is the y-axis into the page. And here we have z-axis of rotation. Here we have an object, okay, with this strange shape. And let's consider it is a rigid body, okay? And this object is rotating around the z-axis, okay? This object, this rigid body, is rotating around the z-axis, okay? This is the axis of rotation, don't forget. So here we have three forces act on the M1 on this rigid body. We apply force F1 tangential acting on M1, and here we have F1 radial acting on M1, okay? And here we have F1Z. So which one contributes to the rotation around the z-axis? This one does not contribute rotation along the z-axis. This one does not contribute to the rotation around the z-axis. Only this one, F1 tangential, can produce a z component of the torque, okay? This will produce this type of movement. And now let's try to find a relation between torque produced by this force and the angular acceleration. So this F1 tangential can be written with this form, M1 times A1 tangential, okay? M1 mass of this object here, this mass particle, and this is the force, and this mass will have certain linear acceleration. And from the last lecture, I know that this linear acceleration can be written in this form, R1 times alpha z. R1 is the distance from the particle to the axis of rotation, okay? So instead of A1 tangential, just use this expression, this one, put it there, and then multiply this part with R1. Let me show with pen, maybe you better see. Just multiply this one with R1 and multiply this one with R1 and take this A tangential, put it there instead of A1 tangential. And then on the left side, we will have this one. On the right side, we will have this one. Okay, what do you see here? This is F1 tangential times R1. This is the F1 tangential. This is the line of action of F1. And this is the lever arm R1. Then this is the torque 1, right? And on the right side, what I have? I have moment of inertia of mass 1, okay? And here I have alpha z, angular acceleration. Then just write this one. So this is the torque produced by this F1 tangential on this mass. This is the lever arm R1, and this gives us the torque, okay? And this M1 R1 square gives us the I1, which we have discussed this one during the last lecture, moment of inertia. And finally, we have this expression, torque applied by F1 tangential is given with torque 1z. This, what is this z? Z is showing that the axis of rotation along the z-axis, okay? And this is the I1 alpha z. This is angular acceleration. Now we have a relation between torque and angular acceleration, okay? This is the torque, this is the angular acceleration. And you can also write in this form. Okay. So here we have the relation now. Here we have an example. Loosening or tightening a screw requires giving it an angular acceleration and hence applying a torque. So you give an angular acceleration to the system, and in order to give this angular acceleration, you have to apply a torque. Okay, this is the torque angular acceleration relation for a rigid body. And now let me continue with the external torques or internal torques acting on a rigid body. Remember the discussion for the astronauts in the space. In the previous chapters, we have considered we have two astronauts in the space, and there is no external force acting on these astronauts, and this astronaut on the right side applies a force, the astronaut on the left side, and this astronaut applies the same force on the astronaut on the right side. Okay, so these are the action-reaction pairs of the forces. And what about the magnitude of the force? Let's say this is A, this is B. The force applied by A on B is equal to minus the force applied by B on A. Okay, you remember this discussion. Okay, but what about the net force acting on these guys? The net force is zero because in the Newton's equations, we only consider external forces. Internal forces are not considered. Okay, so like this one, here we will use the same behavior in the torque. So what about the internal and external torques? Let's consider here we have a rigid body, okay, and we have a particle 2. Here on the left side we have particle 1, and this particle 1 applies a force on particle 2, and this particle 2 applies a force on particle 1. So these are the action-reaction pairs. And what about the torque produced by this force on this rotation axis? And what about the torque produced by this particle 2 on this rotation axis? So the torque 1 on 2 is given with this one, plus F times L. F is force, L is the lever arm, okay? And then torque applied by 2 on 1 minus F times L, okay? Because we have opposite force with the same magnitude, okay? So in total, what about the total torque produced by these two particles with two forces? The total torque is 0, okay? For this reason, we are only considering external torques affect a rigid body's rotation, okay? Don't forget this one. Any question here? Then let me continue with this example. Actually, we have discussed this example in chapter 9, and now we will calculate the cable's acceleration. Remember this example here, we have a disc, okay, and a cable wrapped on this disc, and then we pull this cable with some certain force, okay. This poly has certain mass, and this is the diameter of the poly or disc, let's say, okay. And what is the cable's acceleration? So how to calculate this one? Just draw the free body diagram. Here we have weight of the poly, okay, mg, and here we have force applied by hand, okay, and here we have a normal force. Look at this one. Normal force is in this direction, not along the y-axis. Why? Because this force is pulling to the left side, mg is pulling downward, and then n should be in this direction, okay? normal force. So then how to calculate this cable's acceleration, and what about the effect of these forces? So look at this mg. This is the rotation axis, okay? On the left side, I am showing the rotation axis of the poly. So this is the rotation axis, and weight is applied on the rotation axis. So this mg, this weight, cannot produce any torque because lever arm is 0 for this force. And what about the normal force? Normal force is also applied along the rotation axis. So it can also exert no torque. Then only this force can exert a torque. So this is the line action of the force, 9 Newton, and this is the lever arm, radius of the poly, radius of the cylinder, let's say. Okay, this will produce torque. This normal force cannot produce torque. This mg cannot produce torque because they have no lever arm 0. They are passing through the rotation axis. Don't forget this one. Then what about the net torque? So remember the Newton's second law. I just show you to remind the mechanism. So you are writing this one, right? You collect all forces, and then if the net force is different from 0, you write this equation. And in rotational motion, we have analogy of this one. Let me show you. You have to consider all torques, and you have to write this expression, okay? Instead of m in the Newton's second law, here we have moment of inertia. Instead of linear acceleration, we have here angular acceleration, and here instead of force, we have this one, okay? If you are talking about the total torque acting on the system, you have to consider this one. So now you can write the net torque acting on this poly with n, it is 0. So this cannot produce any torque. Only this one will produce torque. Then net torque can be written like this: F times lever arm, this one, R, and it is equal to I times alpha Z. Okay. So, and what about the direction of the torque? This is the lever arm, direction of the R, and this is the direction of the force by applying right-hand rule. So the direction of the torque is from the board, from the screen to us. Okay, is it true? Counterclockwise. Okay. So then what about the I, moment of inertia? In the last lecture, we have calculated the moment of inertia of different bodies. And for this cylinder, for this disc, moment of inertia is this one. Okay, sometimes within the questions it is given, sometimes it is not given. For this reason, for certain shapes, it is better to keep the magnitude of moment of inertia. And then cable's acceleration is asked, okay? Cable's acceleration, not the angular acceleration. A is asked. So here in this equation, look at this one. I can calculate alpha Z, angular acceleration, torque over I from this expression. Alpha Z is given with torque over I, and the net torque acting on this poly, this cylinder, is given with F times R, and I is given with this expression. Put the I here, 1/2 mr square. Then F is known, total mass is known, and R is known. Then you can calculate the angular acceleration, 6 radian per square second. And remember this equation. This linear acceleration or tangential acceleration here, okay, is the cable's acceleration. Then it can be written with r times alpha z. We have done it during the last lecture, okay? We have done it during the last lecture. So A tangential is given with r times alpha z. R is known, and we have calculated this alpha z. Put these numbers here, then you can calculate the acceleration of the cable, which is given with 0.36 meter per square second. Any question here? Okay, let me continue with example 10.3. This was the example in the last lecture in chapter 9, and we will find the acceleration of the falling block and the tension in the cable. So remember this example we have discussed during the last lecture. Here we have a poly with mass m and the radius of the poly, and this is the block here, and mass is m, and this is the height of the poly, and you release this box from rest from this height, and we have done these calculations in chapter 9, and here what is the acceleration? Acceleration of this box is asked, okay? And also tension in the rope, tension in the cable is also asked. So now let me draw the free body diagram for the poly, for the cylinder, and also for the block or box separately. This is the, in picture B, free body diagram for the cylinder or for the poly. This is the rotation axis of the cylinder, and this is the weight of the cylinder, mg, and this is the normal force, and this is the tension in the rope. So due to this mass, so there is a tension force here. And what do you see here? If you write the net force along the y-axis for this cylinder, what you will find? This poly, this cylinder does not move, okay? So the net force N minus T minus mg are equal to 0, okay? In terms of net force. But what about the net force here along the y-axis? mg minus t, and the block is moving with some certain acceleration downward, okay? So then the net force here along the y-axis is different from 0. And now let me investigate the rotation of the poly, rotation of the cylinder. Look at the B again. This is the rotation axis of the cylinder, and normal force is applied along this rotation axis. mg is also applied along this rotation axis, and there is no torque due to the normal force. There is no torque due to the mg. Only this tension force on the left side produces a torque, okay? And the net torque produced by this cylinder is given with this expression. Force times lever arm, T times R, okay, which is equal to I times alpha. Then what is I? I is given with 1/2 mr square for the cylinder, and then I can write this expression. And what about the net force along the y-axis for this block moving down? Net force along the y-axis, mg minus tension force, which is equal to m times ay. Up to now, is it clear or not? Please let me know if it is not clear. If you cannot draw free body diagram, and if you cannot write these two equations here, then it is not necessary to continue. You cannot do something. For the block, I applied Newton's second law along the y-axis, and I got this expression. And for the cylinder or pulley, I applied the torque equation. Net torque is given with I times alpha z, and only tension force applies a torque on cylinder, then I can write this expression. Here we have AY, you see, AY, and I would like to calculate this AY. I don't know what is it. So instead of AY, I can use A tangential R alpha Z. So this is the AY, and this AY is equal to A tangential, and A tangential is equal to R times alpha Z. We have done it during the last lecture in chapter 9. Chapter 9 is very important to understand the mechanism of dynamics in rotation, okay? So then here we have AY and alpha Z relation, you see? Alpha Z, AY. Then use this expression here instead of AY. Then we can calculate this tension force. Tension force is given with 1/2 MAY, okay? Then just put this T into this expression. Here we have a T, just take this T, put it there, then finally you can get this expression. Then a Y is calculated. Tension can be calculated in this form because here you have calculated AY, put it there, okay, you can calculate the tension force. Any question here? Okay, let me continue with rigid body rotation about a moving axis. So up to now, we have just discussed the rotation. Here, just look at this example. This pulley, this cylinder is rotating, okay? And here, this cylinder or this pulley is rotating. And here, this object is rotating. Here, this bolt is rotating, okay? But it is not moving in any direction. It is just rotating around certain axis. Let's consider car wheels, for example. Here, we have a car and car wheels. Let's consider this car is moving along this direction with certain velocity, and these wheels are rotating. So what do you see here? There is a rotation and also translational motion, okay? Every possible motion of a rigid body can be expressed or represented as a combination of translational motion of the center of mass and rotation about axis through the center of mass. Now just take this wheel here and consider that this is the wheel of the car. It is rotating about this axis with some certain angular velocity, okay? And this wheel is also moving. The center of mass of this wheel is moving with some certain velocity into the direction of the movement of the car, okay? So if you consider this wheel has a rotational motion and also a linear motion, okay? Now we will investigate this type of motion of rigid body. Here you see baton, okay? And this guy drove this baton, and what do you see? This is the bottom of the baton, this is top of the baton, and here top part is here, bottom part is here, okay? So the baton is moving like this, and in addition to that, it is rotating around itself, okay? Each baton here is rotating around itself, and it is also moving up and down, okay? So we have two types of motion here. One is translational motion, this one, and the other one is rotational motion. Now, within this part of my lecture, we will investigate these two behaviors. So here we have a baton. The motion of a rigid body is a combination of translational motion of the center of mass and rotation around the center of mass. So this is the baton here. The center of mass of the baton is moving in this trajectory, along this trajectory, okay? But in addition to that, it is rotating around itself during this movement, okay? It is rotating. So then we have two types of motion: translation of the center of mass along this path and plus rotation about the center of mass, this type of rotation. Then the kinetic energy of a rotating and translating rigid body is, this is the total kinetic energy of the system, 1/2 mv square. This is the mass of the body. This is the speed of the center of mass, speed of the center of mass, speed of the center of mass, plus kinetic energy of rotation around axis through the center of mass. It is rotating around this axis, and then it has certain rotational kinetic energy, which we have discussed during the last lecture, which is given with 1/2 I center of mass, moment of inertia around the center of mass, times omega square. This is the angular speed of the body. Is it clear? Please be very careful in this part, in this transparency. It is very easy to understand, but if you drop from the line, then you can completely miss everything. Okay, now I will investigate these two motions in a single rigid body. The motion of a rolling wheel is the sum of the translational motion of the center of mass plus rotational motion of the wheel around the center of mass. We are talking about, here we have a rod, and here we have a wheel, and this is the center of mass of this wheel, and this wheel is rotating like this, and it is moving in this direction. So this wheel has two types of motion. One is translational motion, this one moving along this direction, and the other one is rotational motion because it is rotating like this. Okay, so let's investigate this behavior. First of all, just consider that this wheel is moving along this direction with some certain center of mass. And I define 5 points on this wheel. This is point 1, point 2, point 3, point 4, and this is the center of mass. So each point on this wheel has certain velocity, the same velocity, velocity of center of mass. If you consider it is just a translation of center of mass, this is moving in this direction. But in addition to that, this wheel is rotating around center of mass, okay? It has this type of rotation on the right side here. So what about the speed here? The speed here is given with V center of mass. If the wheel does not slip during the rolling, okay? This information is very important here. Rolling without slipping. If the rolling without slipping is present in this motion, then the speed of center of mass is equal to R times omega, angular speed of wheel. Okay, we have this relation. Actually, we have got this relation during the last lecture. You remember this one, we have produced this relation, But here we have this additional information. The speed of the center of mass is equal to r times omega. Okay. Then here we have speed of center of mass. 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 And this speed of center of mass is given with r times omega. What do you see here? We have speed of center of mass at point 3 along the positive x direction, let's say. Here in point 1, we have velocity in opposite direction. Okay, then I can write it here with minus v center of mass. This is the translational motion of center of mass. This is the rotation around center of mass. Okay, so during the movement of wheel on a road is this one. Okay, rotational motion plus translational motion. So then what about the combined motion? The combined motion is given with translational motion plus rotational motion. Then look at the speed of each point on the wheel. So here for point 1, for example, we have v center of mass to the right side. And here from the rotational motion, we have minus v center of mass. So in total, in the combined motion, we have 0. So instantaneously, momentarily, this point is at rest, okay, where it contacts the ground during the rotation. And here, the velocity at point 3 is given with 2v center of mass, because from the rotational motion, we have 1v center of mass. From the translational motion, we have 1v center of mass. Then in total, we have 2v center of mass. And look at this one, point 4. We have velocity in this direction. Here in the translational motion, we have velocity in this direction. And here we have this combined velocity. Okay. And the same also for the point 2. We have velocity upward. Here we have velocity along the moment direction. And here we have velocity, which is given with this expression. So this is the combined motion if we have translational motion plus rotational motion. Do you have any question here? Okay, here, let me try to find the kinetic energies. Again, we are discussing this motion, this moment, without sleeping. At any instant, we can think of the wheel as rotating about an instantaneous axis of rotation that passes through the point of contact with the ground. We are talking about this one. This is the ground. This is the wheel. And this is the point of contact for some certain instant, okay? And you can consider that this is a rotation axis for an instantaneous moment, let's say, okay? And let's consider that here in this center of mass, we have an observer. And here at that point, we also have an observer. The angular velocity omega is the same for this axis as for an axis through the center of mass. So this center of mass has certain angular acceleration, okay, because this wheel is rotating like this. And the angular acceleration of this point also equal to the angular acceleration of this center of mass. if you consider that this is also rotation axis for a short moment. You can prove this one like this. There is an observer at the center of mass here. He or she sees the rim make the same number of revolutions per second. We are talking about revolution per second, okay? This finally gives us the angular speed, and an observer at the rim watching the center of mass here. At the rim here, we have another observer, and this observer watching the center of mass, okay? This center of mass will rotate around this rim, and this observer also sees the same angular speed, okay? So what I mean with this sentence, both observers here at the rim or on the center of mass have the same angular speed, okay? Then the kinetic energy of the wheel is given with this expression here. If you consider this point, this is the point 1. Just calculate the kinetic energy. Kinetic energy is given with rotational kinetic energy, I omega. What is I? Moment of inertia for this rotation axis. If you calculate the moment of inertia for this axis and you know the angular speed, you can calculate the kinetic energy. But if you don't know the moment of inertia for this rotation axis, you can apply parallel axis theorem. Parallel axis theorem gives us this expression, moment of inertia about this rotation axis is given with moment of inertia of center of mass plus mass of the object and square of the distance center of mass. We have learned this one during the last lecture, and I have told you that if you know this parallel axis theorem, you can solve many questions in chapter 10. And then just instead of I1, use I center of mass, take this center of mass, moment of inertia for the point 1 minus m r square. Here we have I1 in the kinetic energy formula. Okay, here we have I1. And just take this I1 and use it here. And then we have kinetic energy like this. Instead of I1, we are using I center of mass plus mr square. So just split this term into two parts. Then we have this expression. What do you see here? 1/2 I center of mass omega square plus 1/2 mv center of mass square. So this is the translational motion kinetic energy. This is the kinetic energy due to the rotational motion, which we have given here. Okay, so we got the same result here. Any question here? So then let me continue with rolling with slipping. Here in this condition, we have discussed rolling without slipping. Okay. In case of rolling with slipping, everything changes and you cannot use this relation. Velocity of center of mass is not equal to this expression. Here we have used this relation. If we have rolling without slipping, then you can use this expression. If you have rolling with slipping, center of mass velocity is not equal to r times omega. Let me explain. Here there's a car, and what you see here that this wheel is rotating very fast. It has certain angular speed, okay? It has certain angular speed. It is rotating very fast. But what about the speed of center of mass? The car does not move. It is stationary. For this reason, this wheel has no translational motion, and V center of mass, let's consider 0. Okay? And what about the velocity, tangential velocity at the rim, for example, here, the velocity. This velocity, of course, is given with r times omega, but this velocity is different from velocity of center of mass. So we have no this type of motion. Okay, for this reason, the velocity of center of mass is 0. We have angular speed, and we have speed at this rim, which is given with this expression, but this speed is not equal to the center of mass. Is this part clear? Let me give you these two conditions also. At the beginning, we have a car here. This wheel is rotating very fast. This wheel is rotating very fast, but this car does not move in this direction. Okay, V center of mass is 0. But here we have huge rotation. We have very fast rotation here. We have certain angular speed, and we have also speed at the rim given with this expression. Okay, but center of mass speed is 0. Just consider another case. This car, one car, is coming with some certain speed, and then you apply a force to the brakes, and it is moving in this direction. Let me draw the car. The car is moving in this direction, but since you lock the wheels by applying a force on brakes, then there is no angular speed. The wheels are not rotating, okay? But the car is moving with some certain velocity. So then we have V center of mass, which is different from 0, but angular speed is 0. And also the velocity at the rim of the wheels is 0. Is it clear? Then let me finish with these two transparencies: rotation and gravitational potential energy. Up to now, we have considered motion along a straight line here, translational motion along a straight line, okay? But what happens if an object is rotating and also moving down, or an object is rotating and going up, okay? So in this case, you have to consider gravitational potential energy, which is given mgy center of mass. So don't forget this one. You have to consider also this energy in your calculations if you have movement along the y-axis. Now let me finish this part with this bio application: combined translation and rotation. Here you see a maple seed on the right side, akça ağaç tohumu, maple seed. And if you release this maple seed from rest, it will have this type of motion, rotation around this axis, okay? So there is a weight of the maple seed, and there will be air resistance in opposite direction, okay? So then with the air resistance, since it has non-homogeneous shape, we will produce a net force and a net torque around this rotation axis, and this seed will rotate, okay, during falling down. So this is a bio application combined translation and rotation. So it is rotating around this rotation axis, but it is also moving down, okay? Translational motion along this direction and also rotational motion. Okay, let me continue with example 10.4, speed of a primitive yo-yo. Here, there's a primitive yo-yo which has a massless string wrapped around a solid cylinder with mass m, radius r. This is the radius of the yo-yo. This is the mass of the yo-yo. This is the massless string, massless rope wrapped around a solid cylinder. Hold the free end of the string stationary and release the cylinder from the rest. The string unwinds but does not slip or stretch as the cylinder descends and rotates. Using energy considerations, find the speed v center of mass of the cylinder after it has descended a distance h. So you are holding from this side of the string and this wrapped string is open during this movement. So during this movement, what we have translational motion and we have also rotational motion. This yo-yo is rotating, this cylinder is rotating and also moving down. We have two motions here, so you can use the energy relations and you can solve the question. In addition to that, you can apply Newton's second law and also the net torque acting on the system. You can also solve this problem by using the second method, and within the following part we will do that. Now I just use the energy considerations. So what about the kinetic energy at the beginning? It is not moving, it has no translational motion and it has no rotational motion at the beginning. For this reason, kinetic energy at the beginning is 0. And let's consider that it has certain potential energy. This is the level 0, okay, in terms of y-axis. And we have here certain gravitational potential energy, which is given mgh. This is the distance h. And what about the final kinetic energy? Final kinetic energy is given with translational kinetic energy and rotational kinetic energy. Look at this one. This is the final kinetic energy. This is the translational kinetic energy, 1/2 mv square. This one, the yo-yo is moving with this velocity in this direction. And here we have rotational kinetic energy. Rotational kinetic energy is given with 1/2 I omega square. I is this one and omega is this one, okay, v center of mass of r. This relation is very helpful in the dynamics of rotation and also in the previous part for chapter 9. Don't forget this one. Then if you solve this one, you can find the final kinetic energy of the system, which includes translational motion plus rotational motion, and then put this result here instead of final kinetic energy. What about the final gravitational potential energy? It is 0 because I considered that the final position is y is equal to 0, okay? And then I have this relation. What about V other? Is there any V other here? You can consider the air friction 0. And what about the friction between the string and the surface of the yo-yo? Actually, there is a friction because here we have this information. The string unwinds but does not slip, okay, due to the friction. But this friction does no work, okay? There is no work due to the friction. Then here, mechanical energy is conserved, and I can write this expression. So finally, I can calculate the V center of mass. If you take the V center of mass from this equation, you can calculate this one. So in order to solve this rotational motion and translational motion, I have used the conservation of mechanical energy, and I have used the relation for the translational motion plus rotational motion. Any question here with this example? Okay, let me continue with this example 10.5, race of rolling bodies. In a physics demonstration, an instructor races various bodies that roll without slipping from rest down an inclined plane. They are released from rest and they are moving in this direction. What shape should a body have to reach the bottom of the incline first? So which one will reach the bottom of the incline first? So which shape? This one, this one, this one, or this one? So how to do that? So it is rolling without slipping. It means that there is a friction between these objects and this surface, but this friction does no work, okay? This friction does no work, and we ignore the rolling friction. There is another friction type, rolling friction. In chapter 5, I shortly touch on this as much as I remember, but within this chapter, we will discuss this one a little bit in more detail. So just know that this information here, we have a friction between these bodies and this surface, but this friction does not work, okay, because the bodies roll without slipping. And from the conservation of energy, you can write this expression. What about the kinetic energy of the bodies here? Kinetic energy of the bodies are 0 at the beginning. For each body, kinetic energy is 0 because they are at rest. And they have certain gravitational potential energy, which is given with mgh. And what about the final kinetic energy of each body? Each body is moving in this direction, so they have translational motion. In addition to that, they are rotating this movement, okay? So they have two types of movement. One is translational motion, and they have this kinetic energy related to the translational motion, and they have this energy due to the rotational motion. Let me also write this one with this expression. This kinetic energy related to the rotational motion is given with this expression. So what about I here? I is this one, moment of inertia for each object. So remember that here we have a C. C is different for cylinder, is different for ring shape, it is different for spherical shape or hollow spherical shape. So depending on the shape, here we have different number, okay? You remember from the last lecture. So just put here C. Depending on the shape, you will have different number. So then here we have I, and here we have omega square. We know that V center of mass is given with R times omega if we have rolling without slipping. If we have rolling without slipping, okay, then you can write this expression. Don't forget. And instead of omega square here, just use this expression. Then we have this one. What about the final gravitational potential energy? If you take this level is y is equal to 0, then the final gravitational potential energy for each object is 0. Then finally, you can calculate the center of mass of each object. So what we have here, here we have C, here we have G, here we have H. G is constant, H for each object is constant, then only C changes depending on the shape of the object. So if you put here large number of C, then you will have lower velocity. If you put here small numbers of C, then you will have higher velocity. Any question? So we have solved both examples by using energy relations, okay? And now let me continue to analyze these motions by using dynamics, okay? Again, we have combined translational and rotational motion, and we will solve the motions by using dynamics. What I mean with the dynamics, you write the net external force acting on the body, which is given with m times a center of mass, acceleration of center of mass, and you can write the net torque acting on a rigid body, okay, which is given with I center of mass times alpha z. This is angular acceleration of the rigid body. This is moment of inertia of rigid body about the rotation axis. So by using these two equations, you can investigate combined translational and rotational motion, okay? Here in these examples, we have investigate rotational and translational motions by using the energies, okay? And here, by using the dynamics, you can also investigate, analyze combined translational and rotational motion. Here, I would like to tell you that this rule, this one, is only valid if the axis through the center of mass is an axis of symmetry and the axis does not change in direction. What I mean, here we have a wheel of bicycle, and this wheel is rotating with some certain angular speed, okay? And let's consider this is the axis of symmetry. At the beginning, let's consider this axis into the page, along into the page, and now it is rotating this wheel and the axis is like this, okay? So if you change this axis, then this one is not valid anymore, okay? In order to apply this rule, the axis through the center of mass is an axis of symmetry. So we are talking about a symmetric material, and the axis through the center of mass is the axis of symmetry, and the rotation axis does not change direction. So please keep this information in your mind. And then let me apply this dynamics to the same example here. Here we have discussed this example, and then we have calculated V center of mass just by using the energy relations, and just same example but use the dynamics, okay? For the primitive yo-yo in example 10.4, find the downward acceleration of the cylinder and the tension in the spring. So this is the free body diagram for the yo-yo. This is the weight of the yo-yo, which is given with mg. This is the tension in the string, okay? Here we have the tension, and this is the radius of the yo-yo, r, okay? And this yo-yo is moving down, okay? It has rotational motion and translational motion. So without kinetic energy or potential energy, you can also solve this example by using the dynamics, okay? So just calculate the net force along the y-axis. So we will apply this one, net external force. Net external force, mg, downward, minus t, okay? And here we have m times a center of mass, okay? Yo-yo is moving down. And what about the net torque acting on the yo-yo? So what about this weight? Weight has no torque, okay? Because its lever arm is 0. It is just directly applied on the rotation axis, okay? So there is no contribution to the net torque, and the torque due to this tension force is given with this one, T times R, force times lever arm, okay? And the net torque is given with T times R, and which is equal to I center of mass alpha Z. This expression, okay? Analogy of Newton's second law. And then what about A center of mass? During the last lecture, we have learned that also during this lecture we have discussed V center of mass is given with R times omega Z if we have rotation without slipping. Then acceleration of center of mass can also be written with this expression R times alpha Z. We have discussed this one during the last lecture, okay? This is the relation between linear acceleration and angular acceleration. This is the relation between linear velocity and angular velocity. So don't forget this one. So here we have alpha Z. Instead of alpha Z, just use this one, and then you can calculate the acceleration of center of mass. You can also calculate the tension in the string. Any question related to this example? So just draw the free body diagram, just calculate the net force acting on the system, just calculate the torque acting on the system, and you can solve the problem. Okay, look at the example 10.7, acceleration of a rolling sphere. A bowling ball rolls without slipping down a ramp that is inclined at an angle beta to the horizontal. Here, this is the ramp, this is the ground, this is the beta angle, this is the mass of the bowling ball, and this is the acceleration. What are the ball's acceleration and the magnitude of friction force on the ball? Treat the ball as a uniform solid sphere, ignoring the finger holes. Here we have finger holes, but you can ignore these finger holes and you can consider that the ball is a uniform solid sphere. So we have mg in this direction. We have friction force in this direction. And we have normal force in this direction. Okay, so mg can be split into these two parts. Okay, one is along the y-axis and equal to the n, and the other one is this one. So what about their contribution to the rotation? Let me clean this part. Please look at this object carefully. So this is the rotation axis. Okay, this is the rotation axis. This mg does not contribute to the net torque because it is passing through this rotation axis. This n, normal force, does not contribute to the net torque. Only this friction force contributes to the torque. This is the lever arm. This is the direction of the friction force, and there will be this type of rotation. Okay. And what about the net torque? Net torque, friction force times lever arm, radius of the ball, which is equal to I alpha z. And for the uniform solid sphere, the moment of inertia I is given as this expression, and here we have alpha z. And what about the net force along the x? Let me clean again and show the forces acting on the ball. So here we have n along the y, and here we have mg cosine beta, so they cancel each other. And here we have mg sinus beta and minus fs. Okay, mg sinus beta minus f, friction force. These are the net forces acting along the x-axis on the ball, and they are equal to m times a center of mass. Okay, so instead of a center of mass expression, and then you can eliminate this one here, then finally you have this expression, okay, from this torque relation. Here we have a center of mass, okay, and here we have another equation which includes also a center of mass. If you solve these two equations, then you can get the expression for the a center of mass, acceleration of the center of mass. What was the question? What are Ball's acceleration? We have found it. And what is the magnitude of the friction force? So we have calculated a center of mass, and just take this one, use it there, then you can also calculate the friction force. Any question? We have answered the example, we have answered the question. I hope it is clear. Then let me continue with the rolling friction. And I have two transparencies. With two transparencies, I will finish my lecture. Let me continue with rolling friction. This is another type of friction. In the past, we have discussed the friction forces, different types of friction forces. And this is important in the rotational motion. But let me remind you that in this part of the book, in chapter 10, usually rolling friction is ignored, okay? So, or it is considered that the rolling friction is negligible. But now let me explain what is the rolling friction. If you have a rigid body, what is the meaning of rigid body? During the movement, the shape of the body does not change, okay? And if you have a perfect surface like this, then there is no rolling friction. But if the surface of the rod is not perfect, if there is a roughness on the surface of the rod, or during the motion, if the shape of the body changes, then we have rolling friction. Now, explain the result of the rolling friction. So what do you see here? Here we have a rigid body on the left side in picture A, perfectly rigid sphere rolling on a perfectly rigid surface. So it is perfectly smooth, rigid surface, and this is a perfect rigid sphere, okay? Then this sphere has certain weight, which is given with m times g, and there is a normal force acting on this ball, and there is a friction force if this ball is rolling without slipping, okay? Then what about the rotation, and what about the net torque acting on this ball on the left side? This mg does not contribute to the net torque. This normal force does not contribute to the net torque. Only friction force contributes to the net torque because it has lever arm. So since normal force, line action of normal force is along the rotation axis, and since the line action of the weight is along the rotation axis, they do not contribute to the rotation. Let me say like this, they give zero torque, okay? But this friction force produces a net torque around this rotation axis, okay, if you consider that this is the rotation axis. So, but if you consider on the right side rigid sphere rolling on a deformable surface, let's consider there is a muck on the surface and the surface is very bad, okay? And then what happens? Look at the motion and look at the forces acting on the ball. This is the mg, okay? And this is the friction force. And now normal force is here, okay? Due to the shape of the surface, the total net normal force is along this direction. Then what do you see here? Let me delete and then show their effects to the rotation. So let's consider this is the rotation axis and this is the normal force, line of action of normal force. And this is the lever arm for the normal force, okay? Then within the net torque, we have contribution from the normal force, and normal force will try to rotate this ball in opposite direction. And here we have friction force. It also has certain lever arm, okay? It will try to rotate the ball in this direction, okay? Then they will fight against each other, okay? So then this normal force will produce a rolling friction, okay? You can consider a resistance against the rotation, okay? If there is a deformable surface or if there is a deformable ball, then this rolling friction can be present. But as I told you in the problems within this chapter 10, usually rolling friction is ignored. Any question? Okay, let me finish this lecture with this last bio application of the rolling friction. Here you see a Russian tistel, in Turkish deve dikeni. Okay, one of few organisms that uses rolling as a means of locomotion is the weed called Russian tistel, Calitragus. The plant breaks off at its base, forming a rounded tumbleweed that disperses its seeds as it rolls. So it has many seeds. Okay, so during the rotation, it disperses its seeds, and because a tumbleweed deforms easily, the shape of the tistel can be changed during the rolling. Okay, so then it is subject to substantial rolling friction. Let's consider that this surface is perfect, but the shape of this tumbleweed deforms during the rolling, during the rotation, okay? Then there will be a rolling friction. So we have considered that in this example, we have deformable surface, but perfect rigid shape. But here we have perfect surface, but deformable object, okay? In both cases, we have rolling friction. Then, due to the rolling friction, this plant quickly slows to a stop unless propelled by the wind. So, if there is no wind, it is stopped easily. And if there is certain wind, it has certain moment. And whenever the wind is stopped, then it quickly slows to a stop. So with this one, I have finished my lecture, and in the second lecture, we will continue with work in rotational motion. Take care of yourself.